What's up, XtremeJS? My name's Phil Nash and I'm a developer advocate at Sonar. We build code quality tools that help you avoid and fix bugs and security issues and write clean code. Sonar Lint is a free IDE plugin that helps you as you code, and then Sonar Cube and Sonar Cloud integrate with your DevOps providers to automate your code reviews as part of your CI/CD pipeline. No matter what language or stack you're using, you should give them a try. For many cases, it'll actually be free to use as well. And we'll see a little bit more from these tools as we go through this talk. As I said, my name's Phil Nash, and you can find me all over the internet as Phil Nash on Twitter, on LinkedIn, on Mastodon, or just at my website to find links to everywhere you can find me. Cool, so let's dig into what these top 5 issues in JavaScript projects are. I want to start with where I got the data from. So I just mentioned Sonar Cloud. It's a SaaS solution for static analysis, scanning of your application code. We currently scan hundreds of millions of lines of JavaScript, and what I did was reach into the data from Sonar Cloud to pick out the most common issues that we found in JavaScript projects. And so these JavaScript issues are not runtime issues. We do static analysis. This is the sort of analysis that finds bugs and finds issues based on patterns that we understand are, bad patterns in code, or, potential errors and other things that can go wrong. And so I wanted to dig in and find out what these issues were, what the most common ones were, so I could share them with you. Because ultimately we are here talking about writing clean code. Clean code is code that runs better in production. It has fewer bugs, it has fewer security vulnerabilities, but is also better to work with in development. It's easier to maintain, easier to read, easier to understand. And we think clean code is code that is consistent, that's adaptable, that's intentional, and that's responsible. And so that's what we're aiming for here. I do like to start this kind of thing with a couple of quotes, actually. So this is one from John F. Woods, who's a C++ programmer, a games programmer, back on a mailing list in 1991, when he wrote, "Always code as if the guy who ends up maintaining your code will be a violent psychopath who knows where you live. Code for readability." And I really like this, not because of the image of a violent psychopath reading my code and then coming to find me, but because this is about coding for readability. And that's so important when we're writing code, because we're not just writing code for ourselves, we're writing it for our team, for other people who are ever going to maintain this code. And what I really liked about this quote was that it came from a whole thread in a mailing list, which was about this one kind of issue, the comma operator. And these C++ programmers were arguing over whether they should encourage use of the comma operator in this circumstance so that you can inline 2 expressions into one line of code, so you don't have to use braces around the condition. I quite like this because whilst this is C++ code that they were talking about, this actually also passes as JavaScript code for exactly the same reason. If you only have one line after a conditional that you need to gate with that conditional, you don't need the braces. The issue here is, of course, the comma operator is very small, and if you were to typo that for, say, a semicolon, it's really easy to change the meaning of the code without it being very obvious what's happened here. Now, it's kind of obvious on this slide because the syntax highlighting is now broken, it seems, but in a program or in an IDE, you might not find that, and this is always going to run the second line, and as a JavaScript programmer, I know I've spent many a time searching for a semicolon that's either in the wrong place or not there at all, and they're very hard to deal with like that. And so ultimately, I think this mailing list agreed that the comma operator was a bad idea and was going to make it harder to maintain code. And I think that's cool. That's great to have that discussion. And then I've got another quote. This is from Raymond Chen on the New Old Thing, which is it's a blog that's been going on for a long time on Microsoft. And he wrote design for readability. So now we've got code for readability, design for readability. And he wrote, even if you don't intend anybody else to read your code, there's still a very good chance that somebody will have to stare at your code and figure out what it does. And that person is probably going to be you 12 months from now. And I really like this because not only are we considering like other people that might have to look at this, it's actually you as well. Like, it's easy to understand code after you've just written it, and it's a lot harder to remember what you were thinking when it's a year later and you're trying to decipher whatever you came up with. And so if we're writing clean code, hopefully that is code that is indeed better to work with and maintain, but then because it's easier to maintain, because it's easier to understand, it also is freer of bugs and runs better in production. And that's what we're aiming for. Cool. So what are these top 5 issues? Well, I have a list. I'm going to go through them, but I'm not going to do them in order. So it turns out that when you do look at the most common issues, they are very common. And so you probably won't be surprised by many of these. In that case, I'm going to count them up from 5 upwards, although I'm going to mess around with the order a little bit. And just to make it a little bit more exciting, I've added some confetti to the slides every time we hit something new. So let's start with number 5. The top 5 most common issue in JavaScript, as found by static analysis, is unused assignments. A little bit of confetti. I hope that's okay. Unused assignments. What do I mean by this? Well, this is actually quite an interesting issue. It's the idea that you assign a value to a variable, and then later assign another value to the variable without having used that variable in between. So this is just unclear as to what's going on with this code. Why have we assigned once and then we assign again? Why did we not use that first assignment? Was there a side effect there that we were missing out on or that we needed to use? Clarity is so important when you're reading code because understanding what the intention of the code is helps you to understand what was going through the person who wrote it, what was going through their head when they wrote it. And in this case, it's kind of easy to see that we're assigning and then we're assigning again. But if you've got a 30-line long function and this happens at the top and the bottom, but it never gets used in the middle, it's a lot harder to spot on your own at least. And it still doesn't make any sense when you find it out. And then I did see another pattern of this, which I thought was weird as well. I saw this in some open source code, which is the idea that you'd write a function, and normally they were a little bit more complicated than adding things, but I like to make the examples easy here. But you have a function that not only returns a result, but also assigns it at the same time. Now, it appears that within the scope of this function that result variable is not being used, an unused assignment. But regularly, this kind of result variable is actually in a higher scope, and that this is actually causing a side effect by assigning and returning the result. And so what happens here is we appear to not be using the result of the assignment, but it's being used somewhere else in the application, and that's really hard to reason about. It's hard to know where else it's going to be. And so both of these unused assignments are both confusing to read, and this version particularly is actually difficult to understand what the implication is on the rest of the application, and that's not good. That's not good for our maintainability, but also it's likely to encourage bugs in places as well. And so that's unused assignments. Fairly straightforward. If you assign something, use it. Don't assign things to outer scopes just for side effect purposes. Up at number 4. I think you will agree with me on this one. I hope you do anyway. Double equals and not equals. So the issue is using double equals or not equals instead of triple equals or not equals. And I've got a great graph from another developer to show you why this is the case. As double equals or not equals are all about coercing things into place. They work perfectly normally if you have two things of the same type, but if you try and compare different types of objects with each other, then double equals is going to coerce one into another object, and we get this lovely big table of potential truths out of comparisons. So what you can see here on this table is like down the middle is where items are in fact the same and should be true. You see we have true, true, false, false, 1, 1, 0, 0, 0 is equal to 0. But every other little green square over here is where the coercion turns it into a true as well. So the string 1 is double equal to the number 1, and an array with an empty array inside of it is equal to false, double equal to false. And this is just the stuff of bad JavaScript interview nightmares. Nobody should need to know this. Coercing a value to try and make it equal to something else is not useful for the most part. And that's why triple equals, which has this just lovely, clean, single line of greens down the middle, which is exactly when each thing is when each argument is the same as the other one, is what we want most of the time. And you can see that down at the bottom, an array, an object, They are not equal to each other because they're not the same reference necessarily, and nan is never equal to anything really. But all of this is expected. And one last little tiny bit about double equals is that actually when it's doing coercion between objects, it tends to take 100 times more time. It's 100 times slower than triple equals, which will just false out immediately. And again, it's probably what you want it to do anyway. So I hope you agree with me. Double equals is bad and triple equals is good, and we should not be using double equals in our code bases just because it makes it harder to understand what's actually going to happen. Cool. In at number 3 next, we have sections of code being commented out. Now I don't even have an example for this, just need to talk about it for a second. When sections of code are commented out, if I'm reading a function with a section of code that's commented out in it, not only do I read the function that's written there, I will find myself reading that commented out code as well. And if I'm reading that, I'm trying to parse it and understand what that does. I'm also trying to understand why it's there in the code base still, why it's commented out. Should it be there? Are we re-enabling that at some point? Commented out code makes your code less clear. And we have a mechanism for dealing with code that we might reintroduce sometime later, and that's our source control. That's Git or whatever you might use for that. Commented out code has no place in a code base because it is just simply confusing. Commented out code should be lost. Code should be committed to source control if it's going to be used again in the future, yeah, just use your source control for this. Much more sensible. I'm not going to go to stage 2 right now because that's actually my favorite. I'm going to go straight to number 1, which gets a slightly bigger confetti spray because it is number 1. But it might be something you've seen in your code base. Because yes, number 1 top issue, most common issue, is using var in a code base instead of let or const. Now I know, this is not an enormous bug. This is not going to cause you enormous amounts of trouble. In fact, this is probably a legacy code base issue because we have had let and const in the language for almost 9 years now, but we were using var perfectly fine beforehand. What I would say is that if you come to code that is using var and you can upgrade it to use let and const, you should, because unlike var, a const and let actually communicates. They give us a little bit more of the intention behind a piece of code. You know that when somebody has used const to declare a variable that you don't expect that reference to change. And you know when somebody declares let, you expect that reference to change. That is something we can update over and over again. And that little bit of extra information can cause the difference in understanding a piece of code and not, understanding the intention behind a piece of code. And so if you do find yourself in a file which has a bunch of var declarations, then tidying them up into const and let and using the block scoping capabilities of const and let as well will make your code base easier to understand, easier to manage over time. But those are the 4 ones I decided to get to first because number 2 in this top 5 issues is absolutely my favorite. And it's my favorite because these other ones might seem a little trivial. Especially number 3, commented out sections of code. Yeah, we can just delete them, whatever, it's easy. There's no refactoring there to do, we can just delete them. Job done. But in at number 2 is my absolute favorite because I think it is a problem for the JavaScript community. And that is that the cognitive complexity of functions is too high. And I threw extra confetti onto this one as well because I thought that was important. The cognitive, it'll finish soon, I'm sure. The cognitive complexity of functions is too high. Now, what do I mean by this? Well, you might ask me, what's cognitive complexity? I don't know if you've heard of this at all before. So I'm going to dig into it a little bit. And I'm going to start with a comparison, actually. You see, there are many measures of complexity of code, one of which has been around for a long time, since the 70s, is cyclomatic complexity, and you might have heard of that. I'd expect you more to have heard of that one. But cyclomatic complexity allows you to put a number on a function to tell you sort of how complex it is. Cyclomatic complexity uses some rules to figure out that number, and let me just explain those to you right now. We have this function here, it's a sum of primes. This function is going to take a number and sum up all the prime numbers that are less than that number. And so we have, a couple of loops in here and a couple of conditionals, and it's doing a bunch of stuff. And it's a little bit of a complex function. Like there's quite a bit of stuff going on there. It's not too bad. You can read and understand it, but there's a bit of stuff going on. So cyclomatic complexity scores the complexity of this by 1, it being a function. That's just how this works. It then scores based on where it breaks for loops and conditionals. So we score 1 for this loop, 1 for this loop, 1 for this conditional, and 1 for this conditional, and that scores 5. So that's not too bad. Cyclomatic complexity 5 doesn't seem like a high number, but I just want you to compare that against this function, which is a getWords function, where you pass in a number and it returns you, like if you pass in 1, it returns 1. If you pass 2, it returns a couple. Pass 3, a few, 4, many, and everything else, lots. This is not a hugely complicated, complex function. It's just a big switch statement, which is fine. But cyclomatic complexity says that this scores 1 for being a function, and then it scores 1 for each of the cases in the switch. And when you do that, this function scores 5 points as well. And so under cyclomatic complexity, this getWords switch statement and this sum of primes nested looping conditional statements score the same. And so that doesn't really help a lot, I don't think, when we're trying to deal with how complex we think a function is. In fact, it turns out that cyclomatic complexity actually just measures the number of paths through a function. It comes up with a number of tests you need to write in order to cover every branch. And that is useful, but it doesn't really help us measure how easy it is to understand a function. And so cognitive complexity is a score that was come up with at Sonar back in 2016 as a measure of how easy it is to read and understand a function. Now that's a bit more sort of heuristic based, but it's absolutely useful, and I want to show you why that is. Because cognitive complexity still creates a score, still creates a number that the functions are going to, still creates a number for your function, but it does so in a slightly different way. Firstly, it does so by incrementing for breaks in flow, that is again loops and conditionals. But secondly, it increments a nesting score in the back of its mind. And so every time you increment for a break in flow, you increment by 1 plus the current nesting score. And let's see how that works with our example functions. With our sum of primes, we no longer score for being a function. That's fine. But our first loop scores 1. And then in the back of this algorithm's mind, we increment the nesting score because we're nested now. And we get to our second loop and it scores 2 because it scores 1 for being a loop and 1 for nesting once. And then we increment the nesting score again. And our conditional here then scores 1 for being a conditional and 2 for being nested twice. Now you would increase the nesting again here, but then we drop out of some nesting, and come back to this singly nested conditional, which then scores 2, 1 for being nested once and 1 for being conditional. And ultimately the score for this function is now 8 instead of 5 that we had before with cyclomatic complexity. Meanwhile, our getWords function straight up scores 1 for being a switch statement. Now, switch statement is fairly simple when you think about understanding it. Like, it switches based on the value of one variable or the outcome of one expression, and that's it. If we'd rewrite this as a series of if-else statements, then you'd score for each different if, because the if could be using a different value each time, but a switch is always focused on one value, and so we get this score of 1. So now getWords is 1, sum of primes is 8, and that feels more right about how easy it is to understand either of those. And so then the issue that was raised is that the cognitive complexity of functions is too high. And what does that mean? Well, that means we have a threshold of complexity which these functions breach. And it turns out, well, in JavaScript, we use a default threshold of 15. So when you hit 15 as a function, that is too much complexity, that's too high. And I kind of want to show you a bit of this in action right now. I'm just going to jump out to my editor here. Right here, I actually have the code that is running on the slide deck to throw confetti on some of the slides. And so I'm using Reveal.js, And this is a function that runs on the slide transition end. And you can see that it does some stuff like reaching into the data set of some of the HTML elements of the slide on the page, getting some information out of it, and then ultimately calling a confetti function with some of that information. And there's a bunch of stuff going on, including a big settings object there, but that's not particularly complex. There's a bunch of other things going on. What we can see is I've got SonaLint installed in this editor. And I've got this little yellow underline here, which says refactor this function to reduce its cognitive complexity from 19 to the 15 allowed. Now, I think this is kind of interesting. Like, this is actually like a 90-line long function, although a lot of that is a settings object in the middle. But we've got this long function that we're now saying this is too complex. It's got a complexity of 19. And I think that's really useful because it can now tell me I should go back and reevaluate and maybe refactor this function to make it look nicer. Indeed, what I can do with SonaLint is if I head to the quick fix menu here, I can actually hit show all locations for this issue. And what that's going to do is actually, it shows me everywhere in the function that scores in our cognitive complexity thing. So our first conditional there is +1, and then I've got a ternary conditional here, which is nested once, so we get +2. I've got a conditional here. There's we also score for Boolean operators like that. This ternary here is +3 because it's nested twice. We're back here to a +2. And you can see all the way down the function, there's various places in which we add complexity. Now, we could refactor this in a number of ways. One way might be to actually, invert this conditional at the top, because there's a big conditional that sits around the whole thing. And if we say if confetti is not in the data set, we can just return. And then if we go down to the bottom, we can fix it. And what that's done is, yeah, there we go. We are now, we returned early if we don't have confetti on the data set, and then we can just get about our jobs throwing confetti afterwards. That has reduced it to below 15, but I don't think that's enough. There's actually a lot more we could do with this. There is some duplication in bits of code like this, which reach into the data set and get stuff out or return like a default feature. That is used there and there to get integers, and it's used there to get like an array of things. And so, like, working harder on this, now I know that this is a complex function that if I were to, add something back in that was complex, I might breach the threshold again. We could just turn this into something which is a lot nicer. We extract some helper functions like this integer data attribute or default, which gets an integer out of the data attributes, or this gets an array out. We can extract each of the confetti functions, and then that's the big settings object. And then our slide transition end looks a lot more sensible. We do our early return, we use our extracted functions, and this is a lot more understandable and a lot more easy to deal with. So when you breach that complexity threshold, that is a good time to say, should I refactor? Cognitive complexity is not just a score we're trying to stay under by 1 or 2. It gives us that inclination that we can do more with this piece of code and make it better over time. If we refactor complex code as we come across it, then that is going to make our life and our code bases much better over time. And so those are our top 5 issues, most common issues found in JavaScript. We had unused assignments, we had using double equals, we have sections of code being commented out, using var instead of let or const, and my favorite, cognitive complexity of functions being too high. As a industry, we can work to bring that complexity down in our own applications and make our lives and the lives of our future programmers happier. There are some tools you can use for this. So SonaCloud and SonaCube, as I said, will scan this as part of your pipeline. SonaLint is free and it can go in your editor. If you're using ESLint already and you want to add cognitive complexity as a function, then check out the ESLint plugin SonaJS, which is a plugin that includes a bunch of our rules, including cognitive complexity. So you can add that to your ESLint plugin as well. There are some other links. I'll share these slides with you over at the conference. There's a paper on cognitive complexity, that blog post by Raymond Chen, which I really like, a whole bunch of rules that we apply against JavaScript and Sona, and then also the source code to this Reveal.js confetti plugin as well. So ultimately, we're looking to build clean code, right? And I want you to clean as you code. As you find these things, get them refactor those complex functions, code for readability, and code for your future self. Again, my name's Phil Nash. Thank you so much. Again, I'm a developer advocate at Sona. I hope you enjoy the rest of the conference. Thank you.